Hi, my name is Jim, and we're going to be discussing a circuit analysis technique referred to as mesh. And what I've done is I've taken the same circuits that we covered in nodal, and now we're going to solve them in mesh and superposition and graphically, and also by determinants. So you're going to have multiple tools to deal with this kind of circuit. So in mesh analysis, and this is the same schematic we used in nodal, is we draw mesh currents I1 and I2, which are in the clockwise direction. Now these mesh currents may or may not be equal to the physical currents. So in a way, this is kind of like a model that we're going to use to solve the circuit parameters. And once we determine what the voltage is at point node A here, is that it's a very simple matter to determine the three physical currents flowing in the circuit. So what we have to keep in mind here is the sum of the voltage rises equal to the sum of the voltage drops, and a current flowing plus to minus is a drop, and a current flowing minus to plus is a rise. So this would be a rise, and these two resistors, the current times the resistance here, would be a drop. Now what's very important in setting up the equations, and that's the first part of this, is to get the two equations, and then the second part is to solve them, is you have to be very, very careful with signs. So what you absolutely want to do is put down the polarity of the drops in each loop. In loop number 1, it's plus to minus, because this is the direction that the current is flowing, the mesh current. And in loop number 2, it's plus to minus in the opposite direction because the current is flowing up. So if you don't get that right, just about guaranteed to get an incorrect answer. Then the current flowing through this, of course, would be just I2 plus to minus, and this guy would be I1 plus to minus. So proceeding here, we're going to set up our two equations, and to start with here is what we see is a minus to plus rise as the current is flowing through the source. So I'm going to say that that rise is 22. Here we have a plus to minus, that's going to be a voltage drop, and that's the resistor value 2K times I1. Now we have to be very careful here because I1 and I2 are flowing through the 8K resistor. So that current would be 8 times for this loop I1 minus I2. And you can kind of see from the polarities there that the voltage drops are going to in fact subtract. So this is our starting equation here, and then what we'll do is distribute the 8, easy enough, and then writing the equation in the right form, we have 10 times the first variable I1 minus 8 times I2 is equal to 22. Now we have to do the same for the second loop here, so we'll start out at this point. It doesn't really matter where you start. So this is going to be 8, and since we're in this loop, plus to minus would be a drop, and since the current in loop 1 is flowing in the opposite direction, we would be subtracting 8 times I2 minus I1. Then we have 3 times, and this would be 3K here, 3 times I2, that would be this guy, and where mesh current is flowing into the positive terminal on a 12-volt source. So that means that that source is going to be treated as a voltage drop for this. So we have plus 12, and that's going to be equal to 0. Now combining terms and getting it in the same form as this, we end up with negative 8I1 plus 11I2 equals negative 12. So once we get these two, what the next step is to solve them. So first thing I'm going to do is solve it by substitution rather. And what I choose to substitute is really quite up to the individual. And when we do substitution, we take one equation and solve it in terms of one variable. So we'd end up with I1 equals something with an I2 in it, or I2 equals something with an I1 in it. Then we go back, plug those into either equation, and we can solve for one of the variables I1 or I2. Once we get that, substitute that back into the equation and solve for the other variable. So the mathematics isn't difficult, but the probability of dropping a sign making a mistake is quite high, so you have to give attention to detail. So I chose equation number 2. Doesn't matter. And in equation number 2 we have negative 8I1 plus 11I2 equals negative 12. And what I want to do in this, again, I could solve for I2, but I chose I1, is to isolate that variable. So in doing that, I have negative 8I1, and I'm going to work through this step by step. And I'm moving this over to the other side, so that'll give me negative 11I2 minus 12. Then just to get rid of the negative signs here, I'd multiply both sides by negative 1s, clean it up a little bit. Don't have to, it'll work out either way. So that gives 8I1 equals 11I2 plus 12, and then dividing both sides by 8, I end up with I1 equals 11 over 8I2 plus 12 over 8, and then solving for I1, it equals 11 over 8I2 plus 1.5. So what I've got is I1 defined in terms of I2. So we're going to take this guy and go back and substitute him for I1 in one of the equations. So I've just written down our two starting equations for reference, and I've elected to put that into equation number 1. So here we have 10I1, and from our previous calculation, I1 is going to be equal to this. Minus 8I2 equals 22. Distributing the 10 is 110 over 8. I2 plus 15, that's this guy, minus 8I2 equals 22. Combining like terms here, what I did is I turned this into a decimal, 18.75, and other than that, everything's the same. Combining like terms here gives 13.75I2, and that would be these two terms here. And then subtracting 15 from both sides gives 22 minus 15. That's that guy. And then finally dividing both sides by 13.75 to isolate I2 gives an I2 value of 1.217 milliamperes, which is correct. So now, since I know what I2 is, I can go back into any equation, doesn't matter, and substitute in this value for current number 2. So I went with this again, equation number 1. 10 times I1 minus 8 times I2 equals 22, and then we're going to put our calculated value for I2 here. Multiplying by 8, 10I1 minus 9.74 is equal to 22. Finally, 10I1 equals 31.74. Dividing both sides by 10 gives us an I1 value of 3.174 milliamperes. So we've got our two mesh currents here, and this doesn't solve our problem. It gets us quite far along, but to solve the problem, what we have to do is find the physical currents, and the key to that is to find what the voltage is at VA. So I've taken from the original schematic this component of it showing I1 flowing down and I2 flowing up, and then I've written down VA equals 8 times the quantity I1 I2. This would be in milliamperes and kiloohms as before, and that simply comes out of equation number 1. Then I substituted in the values that I got. These are the mesh currents, and the total mesh currents when you do the subtraction is 1.975 positive, and then solving for VA I get 15.7 volts. Once I know VA, then all of the other physical currents in the circuit break down just like they did in nodal. That's the key, is finding VA and V sub A, and I won't go through the breakdown of the physical currents. It'd be exactly the same as a nodal. Now, what happens if I selected the other equation that would be on this side? I would have VA equals 8 times I2 minus I1. Well, what that's going to give us is a negative current of 1.975 milliamperes. And 8K times a negative current is going to give a negative voltage. So it looks like that answer is going to be negative 15.7 volts, which is in serious contrast with this. However, I2 is defined as flowing in this direction. So if this side is more negative than this side by a negative 15.7 volts, what that means is this voltage is actually a positive 15.7 volts. So that can be a little tricky, and when you choose your values to determine what V sub A would be, is try to do it in the easiest way possible. Next, we'll talk about solving the problem by the elimination method. And again, I've written down our two mesh equations here for reference. And in elimination is what we do is we wiggle around the coefficients until they're opposites and add them together, which gets rid of one of the variables. So in this case, I chose to eliminate I1. And it's up to you. It doesn't matter which one you eliminate. So what I did is I've taken our two equations here, and I want the coefficients to be opposites, and I realize that if I multiply the first equation by 4 and the second equation by 5, is what I'm going to do is end up with a 40 and negative 40 coefficient for I1. Now, as long as we multiply both sides of the equation by the same number, we're not going to change the value of anything. So in doing that, this is this equation here, and in the subtrahend I have this equation. I guess I really shouldn't say that, the add-in, because we're going to add these. Adding them together, as you see, the coefficient of I1 equals 0, and we end up with 23I2 equals 88. Again, isolating I2 is we have 88 over 23, which equals 1.217 milliamperes, which is the same as what we got before. So now, substituting that in to get the current flow I1 of our mesh currents, is I'm just going to substitute this value for I2. And as you can see, working through this gives us an I1 of 1.174 milliamperes, which was the same value as we got before. So that would be the way to solve this using elimination. Another method is by determinants, and again I've written down our two mesh equations again, and this time I've put coefficients above them, which are standard in using determinants: A1, B1, C1, A2, B2, C2, and I've arranged it in a matrix. Now you might say, how do you know whether this is C1 and B2 and B1 and so forth? And the answer to that is if we laboriously solve that equation without numbers and symbols, and we looked at the steps that we took to do it, we would end up doing the same steps that I'm going to be showing you in a second. So what you need to do is just accept these, and you don't have to memorize them, and we'll discuss exactly how you go about solving this. Now the two lines here means that this is a determinant, and what's going to happen here is, given this, is we're going to multiply these two together and subtract the product of these two, both in the numerator and in the denominator. So populating this with our coefficients then, C1 is 22, B1 is negative 8, see here C2 is negative 12, and B2 is plus 11. Now this is not minus 8. I'm not subtracting anything here. This is, I guess let me make that a little clearer. This just here is negative 8. So when we do the multiplications, that would be this guy, 242, minus this guy, minus negative times the negative is a plus 96. And if I have explicitly written that there, so I'm less likely to make an error. And then we're going to do the same thing in the denominator. We have 10, A1, times, let's see, B2, which would be 11, minus negative 8 times a negative 8, so that'll give us 110, minus, again, a positive 64. So, what we need to do then is just combine these, do the subtractions here, and do the division, and that's going to equal 146 over 46, which produces a current flow I1, and this is a mesh current, not a physical current, of 3.17 milliamperes, which is the same as what we got before. Next, to solve I2, and notice that the numerator is a little bit different, but the denominator is the same. So the good part about this is we can just use the 46 that we calculated from this guy. That would be this down in the denominator, and we don't have to do that calculation. So again, we're going to multiply A1 times C2 and subtract from it the product of A2 times C1. That'll give us a negative 120 minus a negative 176. So the 176 comes from negative 8 times 22. Again, parenthesizing, keeping the signs nice and clean, gives us a negative 120 plus 176 over 46, and then combining that would give us 56 over 46, or 1.217 milliamperes, which is the correct value for mesh current number 2. From here, we can do what we did before and solve for VA by 8K times the quantity, I1 minus I2. So once we get the mesh currents, and in this examples here, and they're the same as the mesh current from before, we're going to end up with the same solution, obviously, for the voltage at node A, and then we can find all the physical currents if we so desire. And then what we're going to do next is look at the graphical approach, and this is going to be approximate, so there's going to be an insertion of a video here that will show a graphical solution.
We are looking at the graphical solution to our mesh problem, and we're starting out here with our two equations, two linear equations, and what I've done is selected a couple points that we can plot, letting I1, which lies on the x-axis, and I2, which is the y-axis, and the points I've chosen have zeros in them to make the selection of the other point easier. I've selected 2 points per line. Realistically, I should use 3 in case I made an error. I wouldn't be able to get a straight line. So I went on to plot these 2 lines, and you can see the points that lie on the I1 and I2 axis here. And when I do that, these 2 lines representing our linear equations form a solution at this point. And if we examine that, what we find is in an ordered pair, we have I1 followed by I2, which is 3.375 milliamperes and 1.35 milliamperes respectively, which is very close to the mathematical solution. Now, it's nice to see the graph of the lines. However, this is an approximate solution, so we really prefer the mathematical solution. So that's what a graphical, which is our 4th type of solution, would look like if we elected to want to do it this way.
Let's look at another example that uses a current source. So in this case, I'm letting my V1 here be equal to 20 volts. Again, I draw a mesh current for I1 and mesh current for I2 as before, and then I very carefully wrote down the voltage drops across all components with respect to each loop. Now, when you see a current source all by itself in series with a resistor here, what you assume is that the internal resistance of that current source is infinite. So in other words, it's a perfect current source, and instead of drawing this, you just assume that that's what it is. Likewise, the internal resistance of a voltage source here, if I were to look actually at the source, would be 0 ohms. And that'll be very important when we get into the superposition method of solving these. So for loop number 1, I have 20 volt rise because I'm going minus to plus again, and it has to be equal to the drops around the circuit, and that's going to be 8 times I1, and since I2 is slowing up, I'm going to be subtracting again, and that'll give us 2 times I1 plus 8 times the quantity I1 minus 14, and then 14 milliamperes is going to be produced by this current source. So what happens is we don't have 2 unknowns in this case. We only have 1 unknown, so that makes our life a little bit easier. Then we can say that we have 20 equals 2I1 plus our 8I1, which is distributing the 8, minus 112. And then we move the constant 20 over to the other side there. So, well, actually I'm moving 112 over to this side, but adding 112 is going to give us the sum of the two. I switched the terms around a little bit. Then we're going to be combining like terms here, so we end up with 10I1 equals 132, and then solving for I1 gives us 13.2 milliamperes in this case. Now once we have that, all we have to do is find V at node A, and again that's going to be equal to 8 times I1 minus I2, right there. 8 times 13.2, which we got here, minus our 14, which is produced by this guy. And then we have V node A is equal to 8 times negative 0.8, which is equal to a negative 6.4 volts, which is correct. Now, notice that I don't have a mesh current flowing through this, and I don't need to have one because everything is covered. All components are covered by the two mesh currents that we have, and that also backs up into the first part of this example. So our next topic will be superposition, and thank you for watching.